Welcome to another unit in the workbook Statistics. This time I'm going to talk about how we can conduct a log-linear regression analysis. Well, what do I mean when I talk about log-linear regression? I mean that we use an equation formed something like this. A more general case we see on the next slide, but here it's the general idea. Y, being the dependent variable, is used as we know it, but x is not in linear form, but the exponent of some kind of exponential expression. So it's the exponent of some other value. Usually we have a parameter in front of this exponential expression and one inside it, so before the b. Maybe in some cases you also have something like plus c, but this would not really be a good way to go because this would conflict with the a. So the a covers everything with plus c here as well. So we can assume this is more the general version of a log-linear expression. So how can we solve this the easiest way? Well, we could start to take the logarithm, in this case the natural logarithm, on both sides. If we do this, we see that on the right we can actually separate the two parts because there's a multiplication sign in between. Whenever we use this logarithm rule for products, we replace the multiplication inside with a plus outside. So instead of this, we get ln a plus ln exponential function of bx. Well, exponential function, natural logarithm cancel each other out. So we could either directly eradicate both of them, or we could do the thing we have here and pull the exponent in front of the logarithm. And then, well, we have ln of e is 1, so it would look like this. So in other words, we have a linear line, we have a linear function here of x. The only difference being we first have to take the natural logarithm of our dependent variable y. And we have to consider that the value a is not reported, if we apply linear regression, as is, but we get the logarithm of the original a, so we have to take the exponential of ln of a of the value which is reported as the intercept here. The b is actually reported as is in this case. So what we're going to do here, we apply the linear or least squares method. First, we're going to logarithmize y. We calculate the logarithm thereof. Then we conduct a normal least squares estimation of the slope and of the intercept. And then we use for the slope b as calculated. And for the intercept, we're not going to use this, but we use e to the power of the intercept. Well, that's more or less everything for the situation that we have an exponential function here. But it could also be the case that this is a different base, that we have a base of p. In this case, we do almost exactly the same, but we're not applying the natural logarithm here. We're just applying, we could say, any logarithm, or if we want to make our life as easy as possible, the logarithm for base p. Still, we could use, with either logarithm, the rule for multiplication for products, can pull the two parts apart, can again pull the exponent in front of the logarithm. That's rules which work for any logarithm. And, well, in this case, we have the base p, logarithm to the base of p applied to p is again 1. So again, it looks similar to what we got before, the only difference being, in this case, it's the logarithm to base p, which is applied to y, and we also have to adjust if we calculate the intercept. So the procedure to conduct here is more or less the same. Calculate the logarithmized dependent variable, estimate slope and intercept via the least squares method, and then take the slope parameter as is, and for the intercept reformulate this. Well, that's already everything there is on loglinear regression. So we simply change the variables a little bit, and then we can conduct a classical linear regression, classical least squares linear regression as we know it. Well, that's it. I hope you enjoyed it. I say goodbye and see you next time.